Okay, hey everybody, it's Sammy, and I'm going to go over the week 2 Friday notes. We actually had to watch a video for this originally for the assignment because Insco is out of town, but the guy who did that video does the simplex method differently. So it shouldn't be too long of a video. I have most of it written out for us, so we're just going to solve the problem below basically as an example. That's pretty much all this video needs. So we want to turn our minimization problem into a maximization problem, and then we would have the dual linear program. And then to solve, I'm just going to use the simplex method. I chose these really small numbers and made it two-dimensional because I just thought that was the easiest. There's no need for us to have like some crazy problem to understand this. So in order to formulate the dual, all we have to do is we take our numbers in our LP right now, and we're going to put them into a matrix down there. So a matrix, if you haven't taken linear algebra, or maybe you did, you just forgot, or you just have never come in contact with it. I highly doubt that by now, but it's just a way we can represent a linear system, and we can manipulate it and do things to it to make it easier to solve. So one thing to remember, so all we do is we take the coefficients in our linear program and we put them into the matrix. Something to note is we actually want to start with those first. So I'm just going to write 3, 2, 8, 2, 1, 6. And then we now put the objective function on the bottom, 2, 4, and then we represent z with 1. And then I'm just going to section this off actually. I think it looks better, and it also helps us remember where our objective function is in relation. So now what we want to do to change this, so this is our minimization problem right now, and we want to make it a maximization. So all we do is we transpose the matrix, and by the way we transpose is you take this row and you make it your new top column. And then I'm just going to color code these so we can understand kind of what we're going to be doing here. And then third one. So all we're doing is like flipping it basically on itself. So now I'm going to have 3, 2, 2 if I'm reading down that column, and now it's a row, and then I'm going to read down the other columns. 2, 1, 4, and then 8, 6, 1. And so now I have my new linear program. And it's important to realize now that we're in matrix form, we have to figure out how to get back into just, regular equation form. It's not super hard. It's just the way we did it here at the top. You take the coefficients, and let's remember, right, this was for x1, that was for x2, and this was like my solution column. So let's remember that that's z right there. So remember, the bottom one is actually our objective function, so we're going to put that one at the top here. So we're going to have 8x1 plus 6x2 is, well, I'll put z right here, sorry, z equals, there we go. And it's going to be subject to these constraints, which are our top two rows. So we're going to have 3x1 plus 2x2. And now we're less than or equal to, because we're now maximizing. It's going to be less than or equal to 2. And then for the orange highlighted row, we're going to have 2x1 plus x2 is less than or equal to 4. And we're almost ready to formulate or solve this problem. Now we have our new maximization. We just need to remember to solve with the simplex method, we need to add slack because these are less than or equal to. So I just denote that with S1. And I'll denote it for this one with S2. Sorry, I'm running out of room. So as you can see in my tables below, I actually went ahead and did this out because, it's just, I wanted to make sure it was correct. But I'll go through kind of and talk about it. So all I've done is I've taken our variables and they're in the top, created a B row. I've labeled the rows R0, R sub 1, R sub 2. And that's how I'm going to denote it over here in my row operations. So basically, if you notice the little pink arrow on top of X1, we start with this as our entering column because it has the most negative value. And so we don't really care about R sub 0 for finding out with the ratio test. All you do for the ratio test, as you can see, you take the solutions or the B column, match it up with its counterpart in X1, and you divide them. So 2 divided by 3, 4 divided by 2. And so as you can see, 2/3 is less than 2. That's the one we want to use as our new pivot. So as you can see, I've highlighted them both in yellow here to help you understand what my thought process was. So now, again, like I said, I'll erase that now. But basically the row operations right here in pink are going to tell you what you need to do to make your new pivot. So if you notice here, this became the new pivot row, right? So I have that 0, 1, 0. So basically, how do I make that top row have a 0 right there, the R1 have a 1, R2 have a 0? As you can see, I did the row operations up here for it. So you can go ahead and pause the video, take a look, write it down. Basically, you just have to manipulate R sub 1 and add it to the other two rows in order to get those zeros above and below it. Okay, so now as you can see, I actually had to do the ratio test again because as you can see where my pink arrow is, I have found a new negative value, negative 2/3. We will repeat this process again until we have no more negative values in the top row. So I'm going to do the same thing I did before. I take the ratio test. And if you notice, right here, I have a 2/3 and a 2/3. They're actually going to just make one. It just worked out that way. And then if you can see when I did here and here, I got -8. So that -8, yes, it is less than 1, but we only care about positive numbers. So only positive. Cool. So as you can see, 1 is our winner for the ratio test, or where I've highlighted in yellow, I have 2/3. So basically, we would multiply that row by 3/2, and that's how you would get the 1 in that column. So if I'm going to show you the next table, I'm going to choose a different highlighting color here. Let's see, what haven't I used? Let's do red. So these row operations right here, oops, those are going to be in relation to this, how I got this row right here. Cool. So, I did 3/2, I got 1. It was nice because both of the values above and below it were already negative, so I just had to add to them. So now, as you can see, sorry, I'm just going to get rid of these. Now, if you can see, we have our new row right here. We have our new pivots. So these are both pivots, right? Because they have zeros below or above them. Yes, X1 does have a 1 in that column, but it doesn't matter because it's not a pivot. So our pivot did change in 2 iterations, and now we have no more negative values. So that's why we don't need this anymore. We're not going to do that because we're finished and there's no negative values in the top. So the way we read this off, I think people, it's kind of confusing sometimes, but basically wherever there is a pivot, that row, the solution in that row, that's what it equals for that value. So our optimal solution occurs when Z, if you notice, is going to equal 6 if I read across R0 at the end. And that happens when X2, if you read across that row, is equal to 1. And then x1 is 0 here essentially because it is not a pivot. The other numbers in these rows, so like you notice there's a 3 where the slack is, or sometimes, so these numbers all tell us different things. We would use it to find its feasibility ranges, shadow prices, etc. Right now, it does have a shadow price of 3 in the top for S1, but there's no shadow price for the second constraint, so that is the only binding constraint. But that's basically all there is to, solving and formulating a dual LP. If you have any questions, you could comment them if you'd like. If this video, the sound doesn't work or something, I did film it on my iPad, so let me know, and thank you.